Okay, now we continue our discussion on sample number 7, example number 7. So we have a single acting, single cylinder positive displacement pump driven at 0.4 revolution per second, has a bore of 200 millimeters and stroke of 500 millimeters. The suction and discharge pipe are both 100 millimeters in diameter. The suction leaf is 0.4 and the suction pipe is 3 meters long. The water is discharged at a point 20 millimeters above the pump level by means of a pipe of 200 meters long, fitted with a large air chamber 20 meters from the pump. Calculate the absolute pump cylinder pressure at the start, end, and mid-stroke time for both suction and discharge, assuming no slip at the pump, and a friction factor of 0.008 for both pipes. Take the atmospheric pressure as 10.3 meters. Okay, so it can be shown like this one. So we have a piston pump here. So this is the stroke, and this is the data for the suction pipe, and this is data for the delivery pipe. So this is the suction height and delivery height. So it will become suction head and delivery head here. So and then the difference is it has air chamber here, but the location of air chamber here is actually located 20 meters from the piston stroke here. It's given in the question, and the rest here is the distance after the air chamber. So for example, we have 200 meter here. So mean the length from here to here is around 180 meters. And then for this one, I think you could imagine that the length of the suction is quite short, only 3 meters long, and the height, the length of the delivery pipe here is around 200 meters, is quite long. And then as we discussed previously, the piston pump or any positive displacement pump could create a very high pump head for our usage. So the main discussion here is actually about the way we calculate the friction about the air chamber here. So previously we know that the friction for the flow after the air chamber must be calculated by using the idea of flow in pipe. So means that from here to here, okay, the friction for this pipe must be calculated by using the idea of major loss. But the 20 meters here need to be calculated by using the equation for the piston pump, the friction equation for piston pump. Okay, so this is the solution. So let's say we start with the suction stroke, and we know for the suction we need to deduct with all the parameters. So the suction head, the acceleration head, and also the friction head. So at start here, so omega t is equal to 0. So we could get that the acceleration head is 1.932 meters here. So and then friction is equal to 0. Okay, I think we already discussed about this. So and then we get the suction, the absolute pressure, the absolute head at the piston at suction stroke at the beginning is 7.968 meters. So and then we could calculate at the end of the suction. So the equation is remain the same here. So we substitute the value. So I hope you could make a revision about this. So and then we could get it is 11.832 meters. And then at mid suction, so we calculate the friction. So and then we could get that the head for the at the mid stroke is 9.823 meters. So and then we need to calculate the discharge stroke. So at the beginning, end, and also at the mid stroke. And then because we have an air vessel there, so we need to extend our equation become like this. So we need to add all the parameters, which is the atmospheric pressure, time the delivery head, time the acceleration for delivery, not time, plus the friction for the delivery according to the piston, according to the reciprocating equation, and also the friction head according to the flow in pipe calculation. Okay, because we have a piston here, so and then we have an air chamber here, and then we have another section after the air chamber. So means that we need to calculate the friction here according to the reciprocating equation, and we need to calculate this area using the steady friction, so which is the major loss. Okay, so we are focusing the major loss first. Okay, so this is the equation. So this is the set of equation. I hope you could make study about this. Okay, so for example, we have the Q here, the flow rate. So it's equal AV, so it is equal ALN over 60. And then we could substitute the A here with pi d square over 4. So and then we could replace the value of N here without 60 because we are calculating the rotation per second. Or we could substitute with the value of omega here. Okay, so and then if you so and then we could A here is the cross-sectional area, so we have the pi d square over 4, and the L is actually the stroke length of the piston, and sometimes we could replace it with 2 pi r. Okay, so and then we could rearrange also the value of Q into A, R, omega, and pi. So this is, I hope you could do this at home, because the idea is Q is equal to A times V, and then we have A, and then we could replace the velocity of V in terms of radian per second. Okay, so and then this is the relationship between linear velocity and the rotational speed. So we have the U, which is in linear unit, which is meter per second. So and omega here is radian per second. So I think you already know the unit for R for the radius is in meters. Okay, so please be careful when you need to use the idea of rotation per minute or rotation per second here. Okay, so this is the means the notes that I hope you could understand, and it's actually the combination of a lot of equation to ease our calculation. So and then for the major loss here, so the equation is F times L over D V square over 2B V square over 2G. So and then we need to calculate what is the velocity. So the velocity can be calculated by the idea of Q is equal to AV. So and then we could calculate Q is equal to A for the piston, and R omega means the speed. R omega over pi means the speed of the piston. So and then it is equal to the cross-sectional of pipe multiplied with the velocity of the pipe. So and then we could rearrange this equation to calculate the velocity of water inside that pipe by using this idea, which is a cross-sectional area for piston times R omega divided by cross-sectional area for pipe divided by pi. Okay, so so this is to simplify our equation for the calculation later on. So then we could conclude that the major loss in pipe in this situation can be calculated by using this idea. And then the value of L minus L here is actually K for us to get the distance after the air chamber to the outlet. So because we know that air chamber is located 20 meters from the piston, so and then the rest, which is 180 meters, is a distance where the air chamber create a steady flow inside that pipe. So means that we need to use L minus L here to determine the length of pipe after the air chamber. So now we could calculate the absolute head. So in delivery, so we need to add all the parameters. So we have the atmospheric pressure, we have the delivery head, we have the acceleration, we have the friction from the reciprocating equation, and also our major loss here. So, and then we have a constant value, which is the atmospheric head is 10.3 and the delivery head is 20. So, and now we are going to calculate the acceleration and this value and also this value, because these two value, okay, it will be influenced in terms of omega. And for steady friction, it is actually occur all the times. Okay, so first we are calculating the acceleration head here. So we are using this equation because we know the value of omega t is equal to 0. So and then we could get this one, 12.88 meters. So and then we could calculate the friction for the delivery here is equal to 0 because the sine omega t is equal to 0. Okay, omega t is equal to 0. Omega is remain in certain value. Okay, please remember that one. So and then we need to calculate the friction that occur. So this friction is actually need to be added all the time, at the beginning, at the middle, and also at the end, because it's create flow inside that pipe, inside the outlet pipe, as a steady flow. So means that every time the flow will give friction to the system. So that's why we need to calculate it, and then we need to add in our question all the time. All the time means when you calculate at the beginning, at the middle, and at the end of the delivery stroke. So again, so we need to make sure that we deduct the area which not covered by the air vessel. So it is 200 minus 20. So we have 180 meters here. So we substitute everything and then we get it is 0.47 meters. So again, you could see here the frictional value in flow in pipe is quite low compared to the reciprocating pump. So and then we get 0.47. So we add all the value here. So we get absolute head at the beginning of the delivery stroke is 43.65 meters. So and then we calculate the head, the absolute head at the end of the discharge stroke. So the equation is remain the same. So and for steady friction, you can use the previous value, which is 0.47. Okay, so here is 0.47. So we just use this value and then we substitute the friction. So I think the friction is 0 here. So and then we get all this, we substitute all the values, so we get it is 17.89 meters. So and then this is at the mid discharge stroke. So this is the calculation for the friction for delivery. So you could get this equation. So and then we could get it is equal to 0.52 meters. So we substitute everything. So and then we could get it is 31.29 meters.